In the previous lecture, we learned about the degree distribution and emergence of the giant component in the Erdős-Rényi model of random network. For a continued discussion in this lecture, we will try to arrange real-world networks based on their mean degrees and total number of nodes and check its implications on the degree distribution and the average path lengths of these empirical networks. In particular, together with a tight degree distribution, we will see the small word nature as a major characteristic of random networks and discuss how well the random graph theory captures qualitative features of real-world networks. All right, we briefly learned about the nature of emerging giant component with an animation in the previous lecture. Starting from isolated nodes, numerous disconnected clusters are formed as the mean degree passes the critical value, which is precisely given by 1. And actually, I didn't talk much about the formation of a single giant component and the technical points related to the cluster size distribution, but according to the previous research, the disconnected clusters eventually merge together to form a fully connected graph when the mean degree exceeds a logarithm of the network size. Then, where are the real-world networks in terms of the mean degree? You see here all of the internet, power grid, science collaboration, and protein-protein interaction are within the supercritical regime, meaning that there is a single giant component with some disconnected small clusters. One noticeable exception is the movie actor network, which is way beyond the other boundary between supercritical and fully connected states. Why is the movie actor network so dense? If you remember, the movie actor network can be represented as a bipartite graph composed of movie nodes and actor nodes, and the links connecting them. Once we project this bipartite to the actor side by removing the movie nodes, this co-starring network leaves the complete subgraphs, making the whole network significantly denser than other networks. One thing I have to mention at this stage is the fidelity of the network data. Actually, you have good reasons to suspect that the raw data to construct a network may have a missing links and even missing nodes. Likewise, you may worry about the contaminated data by false positive links. The former possibility is especially relevant for a protein-protein interaction network. Although the Human Genome Project was officially completed in 2003, if my memory is correct, now almost 2 decades ago, the human proteome still remains dark, and large portion of the proteome remains unexplored because of research bias and varying quality of experimental evidence. Considering that human body contains between 80,000 and 400,000 proteins, and the majority of the proteome is yet to be cataloged, the coverage of a bit outdated data presented here is simply too low to represent the whole network. All these legitimate concerns admittedly affect the exact location of the empirical networks in this bar charts. But regardless of the details, one take-home message from this slide is that the empirical networks are more likely a single giant component with some disconnected debris. Now let's see how well the random graph model GNP describes the real world. According to the UN's World Population Prospects 2022, the world population will hit 8 billion in this middle of the coming November this year. And let's assume that the whole human beings somehow form a fully connected social acquaintance network. Here, I give this small linking probability to make the mean degree 1,000. 1 out of 10 million might sound such a small number, but as you see, this linking probability is big enough to make the network safely in the fully connected regime. If the network forms a GNP graph, so the degree distribution follows Poisson, the coefficient of variation is just 3%. Now, to see how narrowly distributed the individual degrees are, let's consider the maximum and minimum degree in the network. By definition, the maximum and minimum degree nodes occupies only order of 1 out of n nodes. If we use the explicit functional form of Poisson distribution, we can find the maximum and minimum degree as the two solutions to this nonlinear equation. According to my calculation, you may want to double check, by the way, the maximum and minimum degree is given by these numbers. What does it mean? Yes, except for the most and the least connected individuals, everyone on this planet has degrees between 800 and 1200. Is it convincing to you? Probably not. All the humans have such a narrow range of connectivity is simply unbelievable. Okay, now we switch the gear a little bit, and let's think about the path lengths in random networks. Thanks to the findings by Erdős and Renyi and others, we know that the random graph tends to have negligibly small number of loops, as we will see in a couple of slides later when we compute the clustering coefficient of the random graph. And furthermore, the degree distribution is narrow enough to say that almost all the nodes have a constant degree, which is the mean degree of the network. This observation allows us to compute the number of neighbor nodes as a function of distance from the node. So roughly speaking, the sum of all these d-step neighbors should be the total number of nodes n. Right? So here, d max is the network diameter. Furthermore, the sum of this geometric sequence can be approximated as the mean degree to the power of diameter of the network. Inverting this equation, we obtain the network diameter as a function of network size and mean degree. However, this relation actually gives a better approximation to the average distance, because when we compute the average distance, major contribution comes from the most peripheral shell of the nodes. So, the average distance of a random network is now given by the same formula. One prominent feature to remember is the logarithmic dependence on the network size. That is to say, as a network increases in size by 10 times or 100 times, it merely gives an additional distance of 1 or 2 instead of 10-fold or 100-fold increase. We call it small word. At the same time, the denominator, logarithm of mean degree, tells us that as a network becomes denser and denser, the word becomes smaller. If you're not satisfied with my hand-waving argument, this is the reference you may want to consult. A group of Polish authors did a meticulous calculation and showed that the average distance indeed shows the logarithmic dependence on the network size back in 2004. Also, you see that the path length becomes smaller as the mean degree increases. This table shows some basic measures for selected real-world networks, ranging from internet, web, to power grid, to citation and collaboration in science, and to movie actor network that vary in size and mean degree. The coincidence between the mean degree and log n divided by log k here is sort of impressive. The power grid, email, correspondence, and citation network shows a bit bigger discrepancy compared to other networks, but it still remains within the same order of magnitude. Considering the crude approximation we used, this is indeed good enough. As I mentioned earlier, the world population will hit 8 billion. The classical question is the average distance between individuals on this populated world. It was as early as 1960s that an American social psychologist, Stanley Milgram, conducted the pioneering experiments to measure the average distance between people. Long story short, he designed the experiment where people from Nebraska or Kansas send a postal mail to a recipient in Boston. If the sender knows the recipient on first-name basis, he or she sends a mail directly. But in more likely case of no direct acquaintance, the sender should find a person who is likely to know the recipient, and the procedure continues until the letter finally reaches the recipient in Boston. Some letters reached the final recipient in as few as 1 or 2 hops, while others in as many as 9 or 10 hops. Averaging over these chains, the distance falls around 5.5, roughly 6. Hence the expression 6 degrees of separation. Although Milgram himself never used the term, and there are a few methodological criticisms of his experiments, this was surprising to the contemporary people. It also has been widely recognized as the first empirical study to measure the distance in social networks. A modern version of Milgram's experiment was conducted in Facebook, which shows similar results. It shows shorter average distance, and that's not a surprise, considering this hyper-connected world. In everyday life, our sense of distance is based on our experience with Cartesian coordinate system. Particularly in these regular lattices, the system size scales as the distance to the power of the embedding dimension of the lattice. By converting these relations, we get a general result that the distance scales as n to the power of the inverse of the embedding dimensions for regular lattices. Yes. On the other hand, we now learn that the average path length in random graphs scales as logarithm of the network size instead of power law. To see this scaling behavior more clearly, if we redraw the same plot in double logarithmic scale, log d versus log n, the distinction between regular lattices and the random graph becomes more conspicuous. And because the large n behavior of the average distance can be considered a power law with zero exponent, the natural inference by analytic continuation is that the embedding dimension of random graphs corresponds to infinity. If you imagine the world social network formed two-dimensional lattice because of geographical constraints, the average distance would be the square root of 8 billion. That is 90,000. I guess the implication of small world is now clear. Again, for the world's social network, if we plug the total population size and a hypothetical mean degree into the distance formula for random network, we have this short average distance. But probably more meaningful outcome would be the reverse calculation of the mean degree based on the empirical 6 degrees of separation. So by plugging the number 6 as the average distance, we get the average number of neighbors, which is 45. Right? The same measurement was conducted for the web, which shows some different numbers, somewhat longer distances compared to the social networks. According to the recent research in computer science, the large-scale topology of World Wide Web is characterized by this so-called a bow tie structure. Regardless of the detailed structure of the web, as it explosively grows during the past decades, the average path length increases quite significantly. Then a natural question is, why web has such a long average path length? An insight from the distance formula here is that web grows so fast, while the mean degree stays more or less the same as before, but the web is still a small word, in a sense that its average path length is dependent on the network size only via its logarithm. In the next lecture, we will see more discrepancies between the world of random graphs and the real-world networks, including the clustering property, which will be the starting point of new discussion on scale-free networks or power law.